So in the last lecture we saw Andrei Korolyev's equation dp by dt equals p times capital T, where p is population, t is technology, and little t is time. And we now know what this thing, the derivative, is and where it comes from and why we write it like this. And we also know how, if we're given a formula for p, we can calculate this thing dp by dt, which we said is finding the derivative. But the problem with this equation is that we know what dp by dt is, and what we want to find out is p. So we want to know what the world population actually is if this is the formula for its rate of change. So we want to go from dp by dt back to p, which is, in other words, finding the antiderivative. Now, finding the antiderivative is not conceptually very difficult. In our case that we've been looking at, we had the formula for p was t squared, and we know that the derivative of that is 2t. That's what we worked out. And so if that's the derivative, then the antiderivative of 2t is t squared. And at the moment we only have this one particular example, but in the rest of this lesson, as I promised, we will be looking at many other possible functions and what their derivatives are. And so over here we'll have a whole load of functions and we'll know what their antiderivatives are. So if we see a particular formula for dp by dt, we'll be able to work out what p is, just finding the antiderivative. And the rest of this lecture is just going to explain the notation we use for working with antiderivatives and some other special features of it and how we use it. So let's get on with that. Okay, so I've put up a table like we had before, where we've got the time in millennia, 0, 1, 2, 3, 4, etc. And this time, instead of being given the values of p, we're given the values of the delta p over delta t. We're given the values of the derivative. And we want to find out what the population p is. So what we want to find out then is what the changes in population were at each step. So to do that, we've got the rate of change of population. To find out the actual change in population, we've got to multiply by the time taken. So the situation is where we know what the speed is. It was 30 miles an hour. We need to know how long we were going for to work out what distance we covered. So we know that the population was changing at the rate of 1 here, and the time step is 1 millennium. So let's write down what the time steps were in each case, and this is, as before, always very easy. It's just 1 all the way down because of the way I've constructed the table. So given the time steps, we can now work out what the change in population was at each time step. So if the rate of change was 1 and the time step was 1, then it's 1 times 1, so that the change in population was 1. And then here the rate of change of population was 3 million people per millennium, and the time step was 1 millennium, so we added 3 million people. And here the rate of change is 5 million people per millennium, the time step is 1 millennium, so it's 5, and then 7, 9, etc. And those are the changes in population. But what we want to find out is the actual population. Well, let's assume we start at 0. And now notice I have made an assumption there, and we'll come back to that. But we'll assume we start with Adam and Eve, so just 0 to the nearest million. then the change in population in the first millennium was 1. So we started at 0, we've added 1 million to the population, we've now got 1 million. At the second step, we've added 3 million. The change in population was 3. So we started then with 4 at this time step, we've added 3, we're now up to 4 million. And then the next time step, we're adding 5 million. So we've got 4, it's now taking it up to 9. And then we're going to add 7, 16, and so on. So given our delta p by delta t, we can work out the population. It is, what we do is we find the changes in population and then we just add them up. So the population at this time here is just all the differences so far added together. So it's 9 because it's 1 plus 3 plus 5. And then it's 16 because we add up 1 plus 3 plus 5 plus 7 and so on. So I want to look at that in another way as a chart. So let's draw that. Okay, so what I've done here is I've plotted time along here and delta p over delta t up here. And I've drawn these bars because the time step corresponds to the width of a bar, that's delta t, and the delta p by delta t at any point is the height of the bar, so that's what's up the vertical axis. So this is delta p over delta t, the height of the bar. So what we're doing here is multiplying the rate of change times the time taken to get delta p. Well, when we multiply delta t times delta p over delta t, we're finding the area of this rectangle because it's the width times the height. That's the formula for a rectangle. So the area of this rectangle corresponds to the increase in population delta p. And then, as I was saying, when to find the population at any particular time, we're adding up the areas of all these rectangles. We're adding up the delta p's to get the population. So, it was 1 plus 3 plus 5 gives us a population of 9 at this point. Now, we've shown the delta p going up in these steps, but we also remember, hopefully from the last lecture, that the exact formula for dp by dt is 2t if the population is given by t squared, as it is here. So the exact rate of change is not just going up in these jumps, but is this smooth line 2t. And when we're looking at these bars and finding their areas, we're not actually quite matching the way dp by dt actually varies. We're just looking at it at these sort of very coarse steps. And so we could be a bit more accurate about it by taking smaller steps. So let's have a look at that. So in this case, with smaller steps, delta t, we're finding the width is this little delta t. Remember, we use little delta to show it small steps. The height is this little delta p by delta t, and the width, the area of each rectangle is little delta p. And you can see now that because we're taking smaller steps, we're fitting much more closely to this line. And what we're finding, when we're finding the areas of all these rectangles, we're basically finding the area that's underneath this line. It's still not completely exact because, we're still using finite steps, so there is a little bit of overlap. But we're basically finding the area of this triangle here underneath this line of 2t. And we know that we can kind of get as exact as possible by making delta t as small as possible. And we said last time, basically 0 or infinitely small. So let's have a look at that. Okay, so now taking it to the limit where we make these bars as narrow as possible, so delta t shrinks to 0, which we write as dt, an infinitesimal. The width of each bar is dt. The height now is using the exact formula for the derivative, dp by dt, and the width of, the area of each infinitely narrow bar is dp. But again, we're just adding up all these dp's to get the total population at a particular point. And because we now got them infinitely small or infinitely narrow, they're going to fit exactly under the line. So we're now exactly calculating the area under the line. And now going back to this, we can write a formula for how we're finding the population. We're saying that the population is found by adding up all these bars, so the areas of all the bars. So let's give a bit of space here. So the population is the sum, and we use the Greek letter S to represent the sum, sigma, capital sigma. The population is the sum of all those areas, delta p. We find a population just by adding up those areas, and that gives us p. And we also know that these delta p's, can also write those as delta p over delta t times delta t. That's how we found the delta p's. We multiplied delta p over delta t times delta t, and clearly the delta t's cancel and gives us delta p. So the population is found by summing up the delta p's, or in other words, by summing up the rate of change times the time step at each step, the duration of the time step at each step. And the same applies here then. The total population is going to be the sum of these smaller increments, delta p, these areas of these narrow bars, which is equal to, in the same way, delta p over delta t times delta t, using small increments. And so for the last one, it's going to be p equals the sum of these infinitely narrow dp's, which is the same as the sum of dp by dt times dt. Now the thing is here though, that this is not a real sum. We couldn't put this in a spreadsheet, for example, because these are infinitely narrow. So there's going to be infinitely many of them under this line. And, we couldn't have an infinitely long spreadsheet. We could put these into a spreadsheet. There's going to be a finite number, as we've got here, to get up to 8. We've just only got 8 points. And so we could certainly put those delta p's into a spreadsheet and add them up. We could do here as well. It might be a longer spreadsheet, but there's a finite number of them. We could certainly get those in a spreadsheet, but not when we become infinite. We can't. It is not a meaningful sum that we can do. So to represent that, we don't use this Greek sigma for the sum. We use a letter S. Get rid of that as well. So we're not going to use this a sigma for the sum. Just the same as when we went from these finite bars to the infinitely thin ones, we went from using Greek letters to Roman letter D. We'll use a Roman letter S here, only it's not going to look like an S that we're familiar with, but it's very elongated, but that is a letter S, and similarly here. So it's standing for the sum. But what we call this is the integral. So this is the integral of dp, the sum of dp, and this is the integral of dp by dt with respect to time t. And this process of finding the population by doing this infinite sum of dp by dt is known as integration. And we've also seen that the process of integration is equivalent to finding the area under the line here, or it could, in our case it is just a straight line, but it could be any function, and so it could be a strange curve, or yes, or a neat curve, but it can be a curve. So but it will always be that we're adding up the bars underneath it, so we're always finding the area underneath our curve. And so this thing here, this elongated s, is our integral sign. So let's get rid of that and write up this integration symbols again and have a look at those in a bit more detail. Okay, so we were just looking at this notation formula that the population is the integral of, or integral dp, which is equivalent to the integral of dp by dt dt, the integral of dp by dt with respect to time t. And we don't really need this middle part. That's really just showing where this comes from, but the situations we'll face is where we're given dp by dt and we want to work out p. So we don't really need that, it just explains why these two are equal. So again, let's get rid of that. And write p is going to be the integral of dp by dt dt. And we have an example of that then. We know that when p is t squared, dp by dt is 2t. That's what we saw in the last lecture, and I've already mentioned it in this one. So in other words, the integral of 2t dt is t squared. If dp by dt is given by 2t, we know that the population, when we form this infinite sum, will fit the formula t squared, and that's what we're seeing here, 0, 1, 4, 9, 16. So we could actually put that the other way round. The integral of 2t dt is equal to t squared. So in other words, somebody comes to you and says, look, I know that dp by dt equals 2t. What's p? And you say, oh, well, I know that. The antiderivative of 2t is t squared. So we're going to have to integrate 2t dt, and the answer will be t squared. But there is one slight catch, which is, as I said earlier, we made a bit of an assumption that we start at 0. But that may not be the case, because we're only told what dp by dt is. We're not actually told what the starting value is, or at least we may be, but that is a piece of information we need to know. But if we're not told it, then we can't actually say for sure what p will exactly be. So let's just put another column on here. It might be, that's p question mark, it might be supposing that the population of the world was already 3 when it started. But it still increased dp by dt by these values. So we'd still work out the same changes in population, but because we started at 3, now we're adding this delta p to 3, not to 0. So add 1 to 3, it's going to be 4. And then the delta p we're adding now to 4 to make it 7. and then we're adding 5 to 7 to make it 12, and so on. But it may not be that we started with 3. We could start with something else, let's say 21, in which case this would be adding 1 to 21 is 22, and then it's adding 3 to 22 is 25, and then 5 to that, which is 30, and so on. So we get the population could be anything at this point. It might be 64 if we started at 0, but it might be 67 if we started at 3, or it might be 85 if we started at 21. We just don't know. But what we can see is that the population will always be the starting value added to these basic squares. So if it's 3, everything in this column will be 3 more. And if it's 21, everything in this column will be 21 more than that. So whatever we started at, we're just going to add that to all our values. So it's some constant. In this case, the constant is 3. In this case, it's 21. So we should strictly write that the integral of 2t dt, the summing up all these small differences, will give us t squared plus whatever we started with, which is some constant. And we just sometimes write that just as t squared plus c, where c is a constant. And this constant is known as a constant of integration. Okay, what I've shown on here is a plot of p against t, and using our existing formula that p equals t squared is what we started with in the last lecture, as assuming that was the formula for world population, and it gave us dp by dt. But when we're finding the antiderivative, going back, we're told now that dp by dt equals 2t, and we're now working out what p is. We can't say that it's definitely p equals t squared, because that assumes we started at 0, which we do not know. So we have to take into account that the p might have had some other starting value. So the constant value of p is this, where it started on this chart. And then after that, it's the same curve. It's the same t squared, but it's shifted up by this constant. So we add that starting value to every value on the t squared curve. So because if we don't know what the constant is, that's why we have to say that some arbitrary constant. Now, if we're told what the starting value is, then we can get a definite formula. If we're told it's 3, then we know this will be p equals t squared plus 3. But we do need that extra information of the starting point in order to work out the exact formula and not just leave it vague as to exactly what it is. But let's suppose we're in a situation where we haven't been told what that constant is. So in other words, if we take 2 times let's say here t1 and t2, the population at time t1 is, we can write as that, and the population at time t2 we can write as that. But we don't know what they are, because we don't know what this constant is. So we've got p of t1 is equal to t1 squared plus c, and p of t2 equals t2 squared plus c. We can't say exactly what they are. We know what t1 is, so we've got that part of it, but we're still in the dark as to what this constant is. But although we can't say what p of t1 and p of t2 are, we can say what the difference is between them. We can say how much population was added between t1 and t2. It's that much. And that does not depend on what the constant is. Whatever the constant is, the difference between them will be the same, because we're just shifting that whole thing up and down. So we can say that the difference in population from 1 to 2 is equal to P of 2, P of 2 minus P of T1. Now we had the formula for finding the population was the integral of dp by dt dt. And the way we write finding the difference in population between 2 points is the same as that, but with the limits of integration, as we call it. We integrate between T1 and T2. So that gives us the change in population between T1 and T2. And as we've said, it's not going to depend upon the constant. The difference between them will be the same. And we can see that over here, because if we do P of T1, so P of T2 minus P of T1, it's T1 squared, T2 squared plus C minus T1 squared minus C, because added, but we subtract this. So we subtract T1 squared plus C gives us minus T1 squared minus C, so the C's cancel. So indeed, the difference between them is just T2 squared minus T1 squared in our example. So when we've got this integral, we don't worry about the constant of integration. And we know that that is equal to P of T2 minus P of T1. Well, the way we write that is the integral of P between, it's the integral of T1 to T2 dP by dt. We write this square brackets, it's P between T1 and T2. And all that means is that's just a shorthand way of writing this. So it just means that's P of T2 minus P of T1. So that is the general formula. If we find the change between 2 points, it's given by the antiderivative taken at those 2 points and the difference between them. And that does not depend on any constant of integration, so we can ignore any constant. We'll get a definite answer. And in our particular example, where dP by dt is 2t, that would be the integral from t1 to t2 of 2t dt equals p. Well, p is going to be the antiderivative of this, 2t, which we now have seen many times, is t squared. And that's taken between T1 and T2. And so what we do is just put the T into this. As I say, it's P of T2 minus P of T1. So that's going to be T2 squared minus T1 squared. And that is what we've already seen up here. P of T2 minus P of T1 in our example is T2 squared minus T1 squared. So this is just the notation that expresses these ideas, and clearly we sort of memorize this way of doing it, that the way we write out the integral, we just find the antiderivative, we put this square brackets with the 2 limits of integration, and then we subtract the one from the other. We substitute that in and subtract the one from the other, and so we don't bother with all these drawings and things, we just memorize that formula and then we apply it. So we had as well the example of 2t here. We knew it was t squared, and so we could get the answer. This is the one special case we know, but we're going to see many other formulas that we could go in here, and we'll know what their antiderivatives are. So we can do this for a whole range of functions that we might meet in theoretical history. And now I'll just sum up. So to summarize, if we're given a derivative, dy by dx, we can integrate it with respect to x to give the original function plus a constant that depends upon the initial condition. And this is known as an indefinite integral. And again, with our derivative dy by dx, we can also integrate it with respect to x between two particular points, x1 and x2, to give the original function taken between the 2 points x1 and x2, which just means the difference between y at x2 minus y at x1, and that is a definite integral. And there's no special magic to doing this. It's just that we just recognize a dy by dx as having a particular antiderivative. So we know what it is a derivative of, and these are just things that we know and we memorize, and so when we see it we can say what y is. So in the one example we've been using, if dy by dx is 2t, we know that that will be t squared. And one of the big trick of integration is that this function here may not be immediately recognizable, and so there are techniques to manipulate this function to get it into one of the forms that we recognize and whose antiderivative we know, and that is what you are taught in a calculus class. And now I'd like to summarize the ideas of calculus that we've seen so far. So firstly, if we have a function y, we can differentiate it to get dy by dx, which is the derivative and corresponds to the rate of change of the variable y with respect to x. And then if we've got a derivative dy by dx, we can integrate it with respect to x, which we write as the integral of that dy by dx dx, and that is the integral, and it corresponds to the cumulative sum of all the changes. Cumulative sum. And it also can be thought of as the area under the curve. As we saw, the area under the curve of dy by dx against x. Now, I've said here dy by dx, that is a derivative, but in general, when we're told that the rate of change is something, it will just be some function. So we could also just write this as just a function y which we would integrate. So we're integrating y dx. So, and y is a function of x. So we just find the antiderivative of this function y. So we don't need to write it out as explicitly do y by dx. It's just a function that we want to integrate to find this cumulative sum, or the area under the curve. And I'll just finish off with a sort of practical example. In the pandemic, people plotted the progress in terms of the number of cases per day. That's against time. And it looks something like this. The cases cases per day were quite small, but then they picked up alarmingly, and then they reached a peak, and then it all kind of petered out again, and they decayed back to a low value or zero. And people also plotted the progress of the pandemic in terms not of the cases per day, but in terms of the total number of cases. So that's against time, total cases. And this looked something like this. There were, had been very few cases, then there was a growing number of cases, and the number of cases was rising alarmingly, and then the pandemic died out and it plateaued, and there were no more cases occurring. Well, this is the derivative of that. The cases per day is the rate of change of the total cases. It's how many new cases were being added each day. So it's the number of cases per day is the rate of change is this way. So this was the cases per day is the derivative of the total cases. And similarly then, the total cases was the integral of the cases per day. It was adding up the cases per day to get the total cases that had occurred so far. So these two are related by those operations of calculus. The total cases, take the derivative, you've got cases per day. If you're told cases per day, you can integrate it to get the total cases.